So there are two ways that we can think about this. One is using a property of logs, and another is using a property of derivatives. I think I'm going to explain it using properties of derivatives because that's a good review for us. Notice that this is an outer function is natural log, and the inner function is 13x. So when I take the derivative of this, I have to use chain rule, where I think of the outer function as the natural log function. So the derivative of the outside function is the derivative of natural log, which is 1 over this function, 13x, times the derivative of the inside function, and in this case the inside function is 13x. So the derivative of 13x is just 13 dx. And notice that that means that these 13's actually cancel with one another, and we're left with just 1 over x dx. And if you wanted to, well, I'll just leave it like that, because there's no reason for you to have to review log properties that you may or may not remember. Again, this is fortunate because we actually have a 1 over x lurking in this problem. I can rewrite my original integral as 1 over x times the sine of the natural log of 13x dx. And that means that the 1 over x piece and the dx piece become my du, and this becomes the integral of the sine of u du. I'm going to go ahead and integrate this. The derivative of sine is cosine, so that means that the integral of sine is negative cosine of u plus c. But I don't want to leave it in this final form with a u. I want to go ahead and plug in my original u to get negative cosine of the natural log of 13x plus c. And the final problem that I want to talk about is number 13. And again, it's difficult to see which one of these pieces I want to be my u sub. One thing that I do sometimes when dealing with trig functions is I rewrite this as the tangent squared and secant of theta squared d theta. So how am I going to figure out which u to use? One thing that you can notice is that when I take whatever my u is equal to, the derivative of that has to be lurking somewhere in the problem. And we have memorized now that the derivative of tangent is secant squared. So if I let my u be equal to tangent of theta, then my du is going to be the derivative of tangent, which is secant squared theta d theta. And that's exactly this end piece. So it's a direct substitution in this case. So that means that it's easy for me to be able to say, aha, I'm going to plug in u is equal to the tangent theta squared. So that becomes u squared, and this whole piece becomes my du. Now I can do my easy integration. Don't forget my integration step. When I integrate this, I end up with 1/3 u to the third plus c. And then I plug back in, well, what is my u? Tangent theta. So I have 1/3 of tangent theta to the third plus c. And this question asked for one final step. They wanted to graph this function to verify our work. The easiest way to do that is to graph it either on GeoGebra or using a calculator. So I'm going to go in and I'm going to graph the original function, which was tangent of theta, actually our x value, squared, times, maybe this is the problem, that how do we type in secant squared into our calculator? Your calculator might not have a secant button, right? So what is secant? Secant is just the reciprocal of cosine. So I'm going to type in 1 over cosine of x in parentheses. I'm going to square that. And when I graph that, oops, my zoom is set to a funny window, but it's graphing it. Maybe instead of watching all that. let's go ahead and graph both functions, because we're going to have to graph both functions. Let's go ahead and graph our antiderivative for our integral here is 1/3, so I'm going to type in 1/3 tangent cubed tangent of x raised to the third, and we're supposed to take our c value equal to 0. So now it's thinking and graphing, and if I zoom in on the center, it should look similar to what you have for options. So I'm going to go zoom standard, and now this picture is going to look similar to what your pictures would look like on the various graphing options. So this wiggly one is our original function, tangent squared secant squared. We know that because it takes on only positive values, which makes sense because both of these are squared, so they have to be positive. And then this one that has the cubic action has both negative and positive values.